All right, welcome back for the second talk of the morning, where we'll have Leone Slavich tell us about Trialitarian hyperbolic manifolds and their geodesic submanifolds.
So today I'll speak about Trialitarian hyperbolic manifolds and lattices. So this is an exceptional class of arithmetic lattices acting on hyperbolic space of dimension 7. And what this class of arithmetic lattices does is mainly getting in the way of proofs of some nice results. By this, I mean that if you go through the literature on arithmetic lattices acting on hyperbolic space, sometimes you'll find some results which are stated and hold for all arithmetic lattices except those of this particular class. And there's a reason for this, which I will try to explain. And every time this happens, you have basically two choices. One thing you can do is pretend that these lattices do not exist. And it's something that many people do, and it kind of makes sense, because actually these lattices exist, they form kind of a narrow class. They exist for just one very particular dimension, which is 7, which is probably not the most interesting dimension of all. On the other hand, if you do that too much, at a certain point, you get kind of bored of doing it. And you want to understand a little bit more how these lattices are defined, how they're done, and if you can kind of extend the results that you know to hold for the other classes to this class. And so, yeah, basically this is what I'm going to do today. The plan is to define these lattices, explain why they are exceptional. Then I'm basically going to state everything that I know about these lattices, which I think is pretty close to what is known in general about these lattices. And in the end, I'm going to speak a little bit about the open problems that concern this class of manifolds and lattices. So let me start. And the first thing that I will do is kind of recall the definition of an arithmetic lattice, because I want to highlight a couple of important aspects. So let me give this definition. We say we're going to use the hyperboloid model for hyperbolic space. So the isometry group of hyperbolic space for us is going to be the projectivization of the orthogonal group of the Minkowski form of signature N1. And we're going to say that a lattice gamma inside this Lie group is arithmetic if there exist a few things. The first thing is an algebraic number field. So an algebraic number field K, and we require this field to be contained in the field of real numbers. Okay? And the second thing that we want, this is exactly the field that Kolya was speaking about, so the adjoint trace field. And the second thing that we want is an algebraic group which in my talk is going to be G, an algebraic K group G, whose group of real points is isomorphic to our Lie group, so PO N1R. And essentially what we want is our lattice gamma to be commensurable with the group of integer points of the algebraic group K. Okay, so these are the matrices in G whose coefficients lie in the ring of integers of the field K. So this is exactly the definition that Kolya gave before. The only thing I want to highlight is that two things. Actually, here I have to assume that n is greater or equal to 4, because there's an exceptional class of three-dimensional arithmetic lattices which is actually not covered by this definition, but it's not important for what I'm going to say today. This is something that Kolya mentioned before. And the other thing that I want to say is that I'm not assuming that the group G is admissible, as Kolya did before, but I am assuming that gamma is a lattice. So admissibility follows automatically from the fact that gamma is a lattice. Anyway, this is not really, these are just technical details. Now, the important thing here is the two key players are the field K and the algebraic group G. So these are exactly, as I said, the adjoint trace field of the lattice and the ambient group of the lattice. So sometimes I'm going to call them the field of definition and the group of definition. It is the same thing as the adjoint trace field and the ambient group. It's just a matter of terminology. And the important thing is something that Kolya mentioned, is that the pair given by the field K and the K isomorphism class of the algebraic group G is a commensurability invariant. So I'm going to say that the pair KG is a commensurability invariant. And in fact, if you restrict your attention to arithmetic lattices, this is a complete commensurability invariant. So two arithmetic lattices are commensurable if and only if they have the same adjoint trace field and the same ambient group up to K isomorphism. Okay, so what's the basic idea? This observation leads to the fact that if you want to classify up to commensurability arithmetic lattices acting on hyperbolic space, you really want to classify the algebraic K groups whose group of real points is isomorphic to PO and 1. Okay? If you do that, you're going to get a classification of arithmetic lattices acting on hyperbolic space up to commensurability. In fact, groups which have this property, so groups whose group of real points is isomorphic to PO and 1, are called K forms of the group PO and 1. So what we want to do is, what one would like to do is classify the K forms of the group PO and 1, and this has already been done in the 60s by Titz as part of his classification of semi-simple linear algebraic groups. And it turns out that there are essentially 3 families of K forms of PO and 1. 2 of these are the non-exceptional ones, and they are kind of they give us the arithmetic lattices which we understand rather well, at least from an arithmetic point of view. And then there is one exceptional class, which acts on 7-dimensional hyperbolic space, which is the class that gives us Trialitarian lattices. Okay? So obviously my aim is to define the exceptional case, but just for comparison, the first thing that I want to do is, well, highlight what we have in the non-exceptional cases, the things that we will not have in the Trialitarian case. So what I'm going to do is that I'm going to reintroduce lattices of simplest type. So Kolya did that before, so I'm going to go real quick here. What we need to do is take K, a totally real number field, and then we take F to be an admissible K-defined quadratic form of signature N1, and then we build an arithmetic lattice of simplest type by taking gamma to be the group of integer points of the projective orthogonal group associated to the form F. Okay? So this is an example of simplest type arithmetic lattice. And all lattices which are commensurable in a wide sense to a lattice constructed in this way are going to be simplest type lattices. Okay, so this is probably the class that most people are familiar with. But what I want to say is that in this case, we can explicitly describe some interesting, arithmetic data for our commensurability class. So here, we can describe, and I'm not going to get into the detail of what to describe means, a few things. So first thing, we can describe the ambient group G. Okay? By describing the ambient group G, what I mean is really exhibiting the polynomial equation which define it as an algebraic variety. So in this particular case that I'm considering, G is the projective orthogonal group of F. And okay, let's forget about the P for a moment. The orthogonal group is defined by the, so you just fix the basis so that your quadratic form is represented by a matrix with coefficients in K. And the group G is defined by this equation over here, which tells that the matrix X belongs to the orthogonal group of the form F. Okay? So A is just a matrix representing the form F. And this is clearly polynomial with coefficients in K, because the matrix A has coefficients in K. So we know what this algebraic group is as an algebraic variety. And from this we get, well, in a certain sense, an explicit description of the group of integer points. So at least one lattice in the commensurability class that we are considering. We just look at those matrices which lie in G whose coefficients are in the group of integer points. And quite crucially, we also get a description. So this is the group of integer points. So this represents, well, our lattices in a certain sense. We also get a description, a reasonable description of the group of rational points. So why is this important? Well, clearly, the group of rational points is an invariant of the pair given by the field K in the group G. So it is an invariant of the commensurability class. And in fact, the group of rational points has a geometric interpretation because it corresponds to the commensurator of the arithmetic lattices that we are considering. Okay, and this is clearly commensurability invariant. It's an invariant of the commensurability class. And not only, we also have a further kind of useful thing. What we get is also, and it's kind of easy, an isomorphism, which is also, again, evident in this case, the isomorphism between the group of real points of the ambient group and the Lie group we're interested in, so PO N1R. Okay? Again, in this case, it's easy. It's just conjugation by the matrix which expresses the base change that takes the matrix A to the matrix represented the Minkowski form of signature N1. So just conjugation by a matrix with real coefficients. And this is useful because once you have this, well, what you're going to be able to see is how elements in your lattice, or more general in the commensurator of your lattice, act on hyperbolic space. You take a matrix here in the group of rational points, you map it in PO and 1R, you compute eigenvalues and eigenvectors, and for instance, you're going to know if the element you're considering is elliptic, hyperbolic, or parabolic, and you can compute translation length, you can compute everything, okay? And this kind of knowledge is very useful whenever you want to prove theorems about arithmetic lattices, okay? So for instance, you can use this knowledge to classify totally geodesic subspaces in the non-exceptional cases, okay? Now in the Trialitarian case, we're not really gonna have all these nice things, okay? So the tools that we have to understand the action of our lattice on 7-dimensional hyperbolic space are gonna be way more restricted. And yeah, so basically, this is really the reason why it's harder to study the Trialitarian lattices compared to the non-exceptional cases, such as the simplest type case. Okay, so let me draw a line here. Now that I've reviewed what we have in the non-exceptional cases, let's pass to the definition of Trialitarian lattices. And in order to explain how these lattices are defined, I have to kind of introduce a little bit, give a very simplified version of this classification of semi-simple linear algebraic groups. Okay, so I'll try to make it as simple and non-technical as possible. So what is the idea behind this classification? So we are given G, and a semi-simple algebraic K group. So how do we understand this group? How do we study this group? So its idea is the following. You proceed in steps. What you do, this is it is a group, but it also has an algebraic variety structure. It is defined as the zero locus of a set of polynomial equations with coefficients in K. You look at the complex solutions. So what you do is you consider, first of all, the group of complex points of the algebraic group G. Okay, so the group of complex points is a complex Lie group. And to a complex Lie group, you can associate its Lie algebra. So you look at the tangent space at the identity. It is a vector space, and it is also endowed with a natural Lie algebra structure. So let us give a name to the Lie algebra. So its Lie algebra, I'm going to call it German G, and kind of forgive me for writing a Gothic G in this way, but I cannot do it better. So this is the complex Lie algebra of the complex Lie group given by the complex points of our algebraic group. Okay? And now what you do is, well, this is really the crucial point. This is a complex Lie group, but you have a natural action. So we look at the action of the absolute Galois group of the field K. So I'm going to write this group as calligraphic G, and this is the Galois group of the extension C over K. Okay? We look at the action of this group on the group of complex points, on the Lie group given by the complex points of the algebraic group G. So this action is actually really simple to define. So what is the idea behind? The idea is that G is defined, as I said, as the zero locus of a set of polynomial equations with coefficients in K. So if you take a polynomial, let's call it P, in some number of variables, okay, with coefficients in K, and then you take x0, which is a complex zero of this polynomial, x0. So this is an element of C to the power of n, such that P evaluated in x0 is equal to 0. And you take a Galois automorphism of C over K, so an element sigma of this group G. Well, what you can do is you can take this equation and apply to both sides the Galois automorphism sigma. So from this, you get that P sigma, this is the polynomial where you apply sigma to all the coefficients of P, evaluated in x0 sigma, is equal to the Galois conjugate of 0. But the Galois conjugate of 0 is obviously 0. P is a polynomial with coefficients in K. So its coefficients are fixed by the Galois action. So this guy over here is just P, evaluated in x0 Galois conjugate. So what we have just seen is that if I take an element here and act on it with an element, and actually take its entries and apply to its entries a Galois automorphism of C over K, I'm still going to get an element of this complex Lie group. Okay? So there's this natural action of this group on this Lie group. On one hand, this is a nice action because it is an action by group homomorphisms, okay, by group isomorphisms. So this is nice. On the other hand, it is a really bad action for other two reasons. First of all, this group is huge. It's a very complicated group. The second reason is that this action is nowhere near being continuous. It's going to be highly discontinuous. Okay, so it's not an action by Lie group automorphism. Okay, it's going to look really bad from a differential from the manifold point of view. Okay, nonetheless, this action actually defines the group G because the fixed point of these actions are going to be the rational points of the group G. And these are Zariski dense in G. So really this action is essentially defines the group G as an algebraic K group. Okay. So, well, the idea of TITS is, okay, this is the important thing that we want to understand this section, but this section is very complicated. So we're going to look at something simpler. Okay. So what we do is, well, we do the following. Rather than looking at the full action of G on this complex Lie group, we project it to an action on the Lie algebra of the group G. And this can be done in a natural way. So what Tits does is he says that we should build the root system let's call it phi, associated to the Lie algebra of the Lie group, of the complex Lie group. And what we do, so what is the root system? So this is a bit of a lengthy thing to explain, but in general, this is really the machinery introduced by Cartan. When you have a complex Lie algebra, there is a natural way to associate to this complex, a semi-simple complex Lie algebra. There's a natural way to associate to it a Euclidean space with a finite collection of non-zero vectors. These essentially represent the non-zero eigenvalues of the joint action of a Cartan subalgebra of your Lie algebra, okay? And actually the root system, well, the important thing is that the root system is not a random collection of vectors. It satisfies some very restrictive axioms, which are the root system axioms. And essentially what Cartan did is reducing the classification of complex semi-simple Lie algebra to the classification of root systems. Okay? But the point is that the action of the Galois group, so first of all, you build the root system associated to the Lie algebra, and you consider the Dynkin diagram of this root system. So the Dynkin diagram is essentially, I'm going to say something more, is a diagram that encodes the isomorphism class of the root system. And what happens is that what you can do is that you can project the action of the absolute Galois group to an action, well, first of all, to an action on the root system, okay? And this, in turn, an action on the root system, which is an action by automorphisms of the root system. And this further projects to an action on the Dynkin diagram. So let me call D the Dynkin diagram. You get a natural projection of the Galois action on the Dynkin diagram of the root system. So how this projection is defined is a bit, well, it's a bit technical. So I don't want to kind of enter the details. But all I'm going to say is that the root system can be this root system can be naturally identified to the group of characters of a maximal K torus in the algebraic group G. And the action of the absolute Galois group is going to induce an action on the group of characters of a maximal K torus, which in turn induce an action on the root system, on this root system, which in turn induces an action on the Dynkin diagram. So this is all I'm going to say because it gets technical, okay? But there's kind of a natural way to do it, okay? So in the end, what you get out of all of this is the Tits index of the algebraic group. So the kind of a definition, the Tits index is a symbol, actually, of the form of this form. there are two elements, x and m, where x denotes the type of the root system, the absolute type. So essentially, it denotes what Dynkin diagram the root system has. And m is the order of the image of the Galois action on the Dynkin diagram. So we're going to see an example shortly. Okay. So let's see this example. So let's basically work with an explicit example. So let me go back here. And well, let's look to the case we're interested in. So we're going to look at forms of an algebraic group G, which is a K form of P071. Okay, so this is the setting we're interested. So see, what you see is that if you have a K form of P071, so the field K is real, and the group of real points of the algebraic group G is isomorphic to P071, then, well, you also know the group of complex points. You just have to complexify this real Lie group. So what you get is that the group of complex point is isomorphic to P0, well, I could write P071 of C, but over the complex number, this is equivalent to P08 of C. And the Lie algebra G of this group is what is normally denoted by S08. And this is the algebra of 8 by 8 antisymmetric matrices with complex coefficients with Lie bracket given by the commutator. Okay? So we know who the Lie algebra is. Okay? And what is the root system? Well, the root system of this Lie algebra, I should write C here. Okay? The root system of this Lie algebra is a collection of vectors in R4. So it is a root system which sits in a 4-dimensional Euclidean space. And this is what is normally denoted the D4 root system. So let me write it explicitly. What is the D4 root system? So we keep R4 with the standard positive definite Euclidean scalar product. And the D4 root system consists of the 24 vectors of the following form. Well, you have plus minus 1, 0, 0, and permutations in the entries of this vector. Okay, so it's essentially vectors which have 2 entries equal to 0, and the other 2 entries equal to either plus 1 or minus 1. Okay? And you can also write a basis for this root system, which is what you're going to need to do to write the Dynkin diagram. So this is essentially a collection of vectors in the root system which span the vector space R4 with the property that every root can be expressed as an integral linear combination of the vectors of the basis with all coefficients either all non-positive or all non-negative. And in any root system, you can always build a collection of such vectors. It depends really on the root system axioms. So a basis is given by, well, these 4 vectors that I'm going to write down. With, well, this vector is especially 0, 1, minus 1, 0. And then these 3 vectors over here are 1, minus 1, 0, 0. The second vector is 0, 0, 1, minus 1. And the last vector is 0, 0, 1, 1. So let me get some space. So if you look at these vectors that I have written here, they all have the same length. Alpha 0, this guy over here, forms an angle of 2 pi over 3 with these three vectors. And these other three vectors that I have in the lower row are pairwise orthogonal. So that means that the Dynkin diagram of this root system is this. Okay, so each vertex corresponds to a vector in the basis, and edges correspond to the fact that two roots have formed an angle of 2 pi over 3, and there are no edges if the two roots are orthogonal. So the central root is alpha 0, and then we have alpha 1, alpha 2, alpha 3. Okay, so we're going to have an action of the absolute Galois group of the field on this diagram over here. So let me make a couple of observations, because this root system has several exceptional properties. So the first thing is that perhaps some of you have noticed that these vectors over here corresponds to a vertices of a regular four-dimensional polytope, which is the 24th cell. Okay? This is a kind of remarkable polytope, and one of the remarkable properties that it has is that it is the only regular self-dual polytope, which is not a simplex or a regular angon. So simplexes and regular angons are the obvious infinite families of regular self-dual simplexes, and there's only one regular self-dual polytope which does not belong to these families, and it's precisely this one. This four-dimensional polytope, this is kind of unrelated to what I'm saying, but I think it's worth mentioning, has also a realization as a four-dimensional finite volume right-angle hyperbolic polytope with all vertices ideal, and this is probably the single most useful building block for four-dimensional cusped hyperbolic manifolds. And it has been used by a variety of authors to build interesting examples of cusped hyperbolic four manifolds. But returning to the root system, to the root system considerations, this diagram over here is the only connected Dynkin diagram whose group of automorphism has order greater than 2. So all other connected Dynkin diagrams, which correspond to simple complex Lie algebra, either have trivial automorphism group or have an automorphism group of order 2. And you see that obviously the point here is that you have an order 3 automorphism which permutes cyclically the non-central roots. Okay? So this is really where the exceptionality of this case arises. Okay? These non-trivial automorphisms of the Dynkin diagram correspond to outer automorphisms of this complex Lie algebra. And these are normally referred to, sometimes referred to in the literature, as the Trialitarian automorphism of the Lie algebra G. Okay? And at this point, you probably get the idea of what the definition of an exceptional Trialitarian lattice is. So let me define them, finally. So the definition is as follows. An arithmetic lattice gamma in PO 7, 1 of R is Trialitarian if the Tits index of the ambient group G is 6d4. Okay, which means that the order of the Galois action is 6. So the Galois group acts by the full automorphism group of the Dynkin diagram. So one thing that you may ask is, why 6 and not 3? Okay, because even the Salic permutation of the 3 non-central roots is exceptional, okay? And there's a reason. If G is taken to be a form of P071, well, complex conjugation has to act by the folding automorphism which exchanges 2 non-central roots and fixes the remaining one. Okay? This is because P071 is what is normally called an outer form of the complex group P08. Okay? So just from the fact that G is a K-form of, well, the isometry group of 7-dimensional hyperbolic space, you're going to get that you cannot have a 3 here, you're forced to have a 6. Okay? So normally the Tits index can be represented by the Dinkin diagram together with arrows which represents the action of the absolute Galois group. So this is the Tits index of, the ambient group of a Trialitarian lattice. Okay? So, okay, kind of roughly halfway through my talk, a little bit later, so it's pretty good. So I finally defined these lattices. Now let's see what we know about these lattices. So up to this moment, I just spoke about properties of an algebraic group. So this is nice, but perhaps if you work in geometric structures of manifolds, this is not really what is interesting to you. You might want to know what lattices you get out of this construction, what you can say about the orbifolds or the manifolds that come out as quotients of hyperbolic space by these lattices. And you might want to understand if they are similar to the non-exceptional cases, or if this algebraic exceptionality translates to some geometric or topological exceptionality. Okay, so let me just cite some results which go in both directions. So there are some similarities and there are some differences. So the first thing I'm going to do is cite a difference. And this, I think, is a pretty interesting result. So this is a result by Bergeron and Clausel. And what they say that if gamma is a congruence, this is the key word, Trialitarian lattice, then the first Betti number of gamma is 0. Okay? So what is a congruence lattice? Whenever you have a commensurability class of arithmetic lattices, within that commensurability class, you have a subclass which is given by groups which are defined via congruence conditions on the coefficients of the matrices. And this is in general a subclass of the full commensurability class. Okay? And we call the groups which belong to this rather easy to identify subclass congruent subgroups. Okay? What Bergeron Clausel are proving here is that if you take a Trialitarian lattice and you look at the congruent subgroups inside the commensurability class, they have 0 first Betti number. Now, why is this a difference? It's because this does not happen in the non-exceptional cases. So just to give some context to this result, I want to say that there's a classical actual result by Lee and Milson, which I'm going to reassume saying that, in this way, well, it certainly says that non-exceptional lattices, arithmetic lattices, have virtual congruence positive B1. So I'm going to say it like this. Non-exceptional arithmetic lattices in PO and 1 of R have the virtual so the congruence virtual positive B1 property. What this means is that in the non-exceptional cases, if you fix a congruent subgroup in the commensurability class, you can find a finite index congruent subgroup whose first Betti number is positive. Oh, yeah. Sorry. You're right. So let's say here n is different from 3. So most of what I'm going to say, it kind of becomes different in dimension 3 because dimension 3 is special. Okay, so yeah, this works only when n is different from 3. But okay, this is still kind of a, okay, as I said, dimension 3 is special, but this, okay, kind of says that so in particular what you get is that you have in every non-exceptional class, you have congruent subgroups with positive first Betti number. While in this case, you have no congruent subgroups with positive first Betti number. So this is a difference, a rather interesting one in my opinion. But okay, this also has an interesting consequence. It says that if you one of the consequences of this result is that a Trialitarian manifold cannot be geodesically immersed in any higher dimensional arithmetic manifold, arithmetic hyperbolic manifold. And this again is in contrast with the non-exceptional cases where you can always define geodesic immersions into higher dimensional hyperbolic manifolds. Okay, so this is kind of goes in the direction of showing that there is an exceptional property for these lattices. Now, let's see rather some similarities. And let's look at some similarities. So I basically want to state two theorems. I'm going to call them Theorem 1 and Theorem 2. The first one is joint work with Misha, Kolya, Sasha Kolpakov, and it says this. Well, you wonder if you have totally geodesic immersed submanifolds inside the Trialitarian manifold. What can you have? Well, for sure, you're going to have closed geodesics. This happens in all hyperbolic manifolds, regardless of arithmeticity. You might wonder if that is all, or if there is more. And there's more. So first theorem is that if M is a Trialitarian manifold, so it's a quotient of hyperbolic space by a Trialitarian lattice, then M contains infinitely many. This is actually, the infinitely many part is actually quite trivial. Infinitely many. Three-dimensional, so let me say it like this, finite volume immersed totally geodesic subspaces of dimension 3. And actually, the infinitely many part is easy because the commensurator of an arithmetic lattice is dense. So once you find one totally geodesic 3 manifold, you are going to find infinitely many. So the real interesting part of this thing is showing that there is at least one totally geodesic finite volume 3 manifold. Okay? So this is one thing. Okay, and the second theorem is joint work with Kolya, Hongmin Sun. And it says that, well, I'm going to say it first and then comment it. Trialitarian lattices are not LERF, where LERF stands for locally extended residually finite. So LERF means that all finitely generated subgroups of gamma are separable. Okay, so what we're saying here, yeah?
What is the type of the three manifolds that are appearing?
Sorry?
What is the type?
Of the three manifolds? Well, it's actually the exceptional class that Kolya spoke. So it's not simplest type, and they're not even those of unitary type, or type 2 as Kolya called them. Those are characterized by the fact that their invariant trace field does not contain a subfield of index 2. So this is the important thing. This is rather technical, but the simplest type and also the simplest type lattices and also the three-dimensional unitary type lattices have in three dimensions have the property that their invariant trace field is a quadratic extension of a totally real field. Well, this is not the case for these three manifolds that we get here.
So you cannot get the Bianchi order.
No, it's not going to be. I mean, perhaps you can. Not that. Okay. Okay, you cannot because the Bianchi orbifold is not compact. So yeah, these lattices are all co-compact. But I'm not saying that these are the only three totally geodesic three manifolds. There could be others. This is just the ones that I've been able to find, or that we've been able to find. Okay? So these lattices are not LERF, which means that there is at least one finitely generated subgroup which is not separable. Okay? So which is not the intersection of the finite index subgroups which contain it. Okay? So guess I'm running out of time, as usual. Yeah. So no worries, I'll finish soon. So let me just describe a couple of consequences of these two theorems. So perhaps I won't be able to do much more than this, but I want to basically describe two corollaries. And so basically corollary one is this. So if you take the first theorem that I said there and you combine it with work of Bader, Miller, Fisher, and Matthew, you get that a hyperbolic manifold M contains a quotient of hyperbolic space by a lattice, so is arithmetic if and only if it contains infinitely many maximal finite volume totally geodesic subspaces of dimension greater or equal to 2. Okay, so basically what they show is that if a hyperbolic manifold contains infinitely many maximal finite volume totally geodesic subspaces of dimension greater or equal to 2, then the manifold is arithmetic. For the converse, well, what you want to do is you wonder if an arithmetic manifold contains finite volume totally geodesic subspaces of dimension at least 2. So there are examples of arithmetic three manifolds which contain only geodesics. So kind of their arithmeticity is not detected by their criteria. But from dimension 4 onwards, so yeah, obviously I should say with n, let's say, greater or equal to 4. From dimension 4 on, well, you have, in all the non-exceptional cases, you at least have totally geodesic finite volume surfaces. So you wonder if you have them also in the Trialitarian case, and the answer is yes. So basically you get this result. And the second corollary, you combine the second theorem with work of Hongmin Sun, and you get that no arithmetic lattice in PO and 1 of R, so in the geometry group of hyperbolic space with n greater or equal to 4 is LRF. Okay, again, here the three-dimensional case is a bit special. So three-dimensional, well, actually the fundamental groups of, not only in the arithmetic case, the fundamental groups of hyperbolic three manifolds are LRF. This is essentially follows from the machinery of virtual fibering. In higher dimensions, it turns out that there's a really sharp difference. So fundamental groups of, at least in the arithmetic case of arithmetic hyperbolic manifolds of dimension greater or equal to 4 are non-LRF. Okay? So let me just, how much time do I have? Not a lot. Okay, like 10 minutes. Okay, so let me just basically give a brutal sketch of the proof. Okay? And that is what I'm going to do. And perhaps I'll not discuss the open problems. So the basic idea is, well, this proof. So these are actually two different results in two different papers, but they kind of follow from the same thing, from the same result, technical tool. And the proof is the following. What we do is we look at the commensurator of our Trialitarian lattice gamma, okay, which is actually the group of rational points of our ambient group. So as I said, we don't have a complete description of the group of rational points, but we don't care. What we want to do is simply find a finite subgroup in here and how this acts on hyperbolic space. And this is enough to give us some geometric information. So the point is that there exists a Klein group, so a group K, which is isomorphic to Z mod 2Z times Z mod 2Z in the commensurator of gamma that acts on H7 in the following way. I'm just going to draw a picture. And I'm going to draw a lower dimensional version of, this picture. So the three non-trivial elements in the Klein group are involutions, which act as rotation along a three-dimensional totally geodesic subspace in H7. So there are going to be three copies of H3 sitting inside seven-dimensional hyperbolic space, and each of the three non-trivial elements here acts as an order 2 rotation along this three-dimensional subspace. Okay, so it fixes, each non-trivial element fixes pointwise one of these three copies of H3 and acts as minus the identity in the orthogonal direction. Okay? And the stabilizer of the full Klein group is actually the intersection of these three totally geodesic subspaces, and it is a geodesic. So these three copies of H3 all intersect in a single common geodesic. Okay? So, fine. From this, you kind of get those theorems in a rather straightforward way. So, theorem 1, you notice that whenever you have a finite group in the commensurator of a lattice, that finite group corresponds to an isometry of some finite cover of the quotient of hyperbolic space by that lattice. Whenever you have let's say a hyperbolic manifold and a finite group of isometries, the fixed set of that finite group of isometries is going to be a closed finite volume totally geodesic subspace. So if you have a closed finite volume totally geodesic subspace in a finite cover of a hyperbolic manifold, it's going to project downstairs to an immersed finite volume totally geodesic subspace. So what I'm saying is that in a rather trivial way, when you project these three totally geodesic subspaces inside your Trialitarian manifold, what you're going to get is the same picture with, however, like these three geodesic subspaces become finite volume and intersect somewhere. So what you're going to see is basically the same thing, but there's going to be some intersection and mutual intersection. But each of these subspaces is going to project to a finite volume, totally geodesic subspace. Okay? So this kind of fixes theorem 1. For theorem 2, I'm just going to say it real quick. Well, kind of follows easily from what we have just seen. So what we have is that basically, if gamma is Trialitarian, well, the quotient of hyperbolic space contains two hyperbolic, so just consider two of these totally geodesic subspaces. You have, inside the quotient of hyperbolic space by the lattice, you have two totally geodesic finite volume immersed three manifolds. Okay? And what you get is a morphism phi from, let's say, let's call these two three manifolds S1 and S2. You have a morphism from the amalgamation of these two three manifold groups over Z. Z is essentially the fundamental group of the closed geodesic at their intersection inside gamma. Okay, it comes out of this construction. Now, this is not necessarily injective, but up to passing to a finite index subgroup of gamma, we may assume that this is injective. And in fact, the amalgamation of these two three-manifold subgroups injects as a geometrically finite subgroup inside the Trialitarian lattice gamma. Now, this is kind of a theorem by Sun. He proves that the amalgamation of two hyperbolic three-manifold groups along an infinite cyclic subgroup is non-Lerf, is not a Lerf group. This is because when you take two hyperbolic three-manifold groups and you amalgamate them, you can find in each of the two hyperbolic three-manifold groups a geometrically infinite group corresponding to a virtual fiber, and the image of these two geometrically infinite groups in the amalgamation is going to be non-separable in the amalgamation. So what this tells us is that this group is not Lerf, but this group injects in our Trialitarian lattice, and being Lerf is a property that passes to subgroups. So Trialitarian lattices are definitely non-Lerf. Okay? So I guess that time is over, so I think I'll stop here. So thank you.